Now we're going to be looking at solving systems of second-degree equations. So by second-degree equations, we mean equations that contain x squared or y squared. In this case, specifically, we'll be looking at conic sections, whose equations contain second-degree terms, so x squareds and y squareds. So we'll be looking at what happens if you have two conics and they overlap each other in the coordinate plane. How many points of intersection do they have, and how do we find those points of intersection? So even just looking at something as basic as a line in a conic, how many solutions can you have for a system with a line in a conic section? So, of course, if the line doesn't intersect, then there are 0 solutions. No intersections, no solutions. Then, of course, we can have 1 if it's tangent. Of course, if a line passes all the way through hyperbolas, ellipses, and circles, we can have 2. But if we have two conics which overlap or intersect, we can have up to 4 solutions. So we'll look at 2 methods for solving systems of linear equations. Of course, we'll look at how to solve them graphically by graphing them in the coordinate plane together and looking for those points of intersection, but also we'll solve them by substitution. So solving systems of nonlinear equations. So remember that the graph shows the points of intersection. Those are the solutions. And algebraically, we'll be looking for the points that satisfy all the equations in the system. So here's an example of a place where a parabola intersected an ellipse, and you can see there are 4 solutions here. So remember, when solving systems in general, the way to determine algebraically if a given point is a point of intersection is just to plug it in. If the point satisfies both equations, that is, it makes both equations true, then it must be a point on both lines, or a point that belongs to both graphs. Okay, so let's fill these notes in together. Solve the system of equations algebraically and round to the nearest tenth. One thing to note about these 2 equations, and this is worth talking about, is that depending on the types of equations you have, there are different methods that are good for solving. We've talked about this before when we've solved systems of equations. Sometimes it's good to use substitution, sometimes it's good to use elimination. How do we really determine which is the best method? In this case, because both of these have an x squared term, and both of these equations have a y squared term, we know that we can use the elimination method to get one of these to drop out. If we were solving a system that involved, let's say, a parabola and an ellipse, the parabola won't have an x squared and a y squared term, so we wouldn't be able to use elimination. So it's important to look at the particular problem that you're solving and make a decision about what method to use before you start solving. Okay, so for this problem we're going to use the elimination method. So we're going to take a look at the bottom equation. That's this one. It should be fairly simple to see that in this case, it's not that hard to get the y's to eliminate. Okay, so we're looking here. These y's can very easily be eliminated if I multiply everything in the bottom equation by 2. So that's what I'm going to do. Okay, so now I've multiplied both equations by 2. And now you can see that these 2 terms are going to eliminate each other. Positive 2y squared and negative 2y squared. So I add my 2 equations together. I get 7x squared equals 11. Right here was the resulting sum of those 2 equations. And then I'm going to solve for x. So once I've solved for x, the next step, of course, is to use substitution. So I'm going to substitute this value of x plus and minus 11/7 in to my original equation. Now in this case, because I'm squaring it, the positive and negative values for x don't make a difference. But you should be careful when you are looking at these problems that if you have to plug in positive and negative values, that you substitute them in one at a time. Okay, that helps us find that y squared is 26 over 7. And then because this problem asked us to round to the nearest tenth, I'm going to turn this into plus or minus 1/9. So we can verify that there are in fact 4 solutions. So we have an ellipse intersecting a hyperbola. That's 1, 2, 3, 4 solutions. So our solutions are 1/3 plus or minus 1/9 and 1/3 negative 1/3 plus or minus 1/9. All right, pause the video here if you need to finish taking notes on this problem. Okay, so let's take a look at this inequality. Notice that I've chosen the exact same 2 equations, so we already know how to graph these. One is an ellipse and one is a hyperbola. So let's take a look at the first equation. This is an ellipse, and we want to note that since this is strictly less than, right here, that we're going to have, strictly less than 9, that we're going to have an open inequality, and that means that the ellipse is going to be dashed. Okay, the second thing is that since it's less than, we're going to shade inside the parabola. Now, if you're not sure where to shade, you can always pick a test point. In this case, you can look at the point 0, 0. You can look at the origin. That's an easy point to test. Since 0, 0 satisfies the inequality when you plug it in, we know to shade the interior of the ellipse. So we shade inside. Okay, the next thing we're going to do is look at the graph of 3x squared minus y squared is greater than or equal to 1. This is a hyperbola. And it's greater than or equal to, so we know that our hyperbola is going to have solid lines. Okay, and we can test a point inside or outside the branches of the hyperbola. Okay, and we can go back, we can test the origin. In this case, the origin does not work. So instead of testing between the 2 branches, we're going to test inside. You can think of these as parabolas. And so we're going to be testing inside the parabolas. And so that's where we're going to shade. Okay, so now that we have those 2 items shaded, now we can clearly see that the intersection is here. And here. Oops, I sort of overdrew those. But we would maybe slightly darken the shading, overlapped shading regions, and that's the solution to this set of inequalities. So on the back side of this piece of paper, you have your worksheet for section 10.8. I'd like you to complete that worksheet today. The sub has the key, so you can take a look at that if you need to validate some of your work and have that ready to turn in to me. And also please complete page 659, numbers 13 through 29 odds, in addition to the worksheet. See you on Friday.